Can you see it?
Yes, sir. Yes, sir.
Now, I was considering the long division method for obtaining the inverse Z transform. So, this was the example. Given xz and the ROC is mentioned, it implies that the inverse Z transform will be a causal sequence. So that's why we have to expand it in terms of a power series involving negative powers of Z, isn't it? Involving negative powers of Z. And that's what we did by long division. So we obtained the samples. In example 2, I am perhaps considering the same xz, but now the region of convergence is magnitude of z less than 0.2. It implies that the sequence that is sought as the inverse Z transform, it will be a non-causal, I mean anti-causal sequence. So xz has to be expanded into a power series in positive powers of Z. We have also done that. Did I complete this case last day? Yes. So we obtained the sample values. You can also generate more and more sample values to the left of n equal to 0. Now, here, the third case will be xz having the same expression, but the ROC is a ring-shaped region in the z plane. Magnitude of z greater than 0.2, less than 1. What will be the inverse Z transform? You can well understand that because it's an annular region centered at origin in the Z plane, a ring-shaped region with inner radius 0.2 and outer radius 1. Therefore, the sequence under consideration, the sequence which will be the inverse Z transform of xz, that sequence must be a two-sided sequence. It must have its causal part, causal component, and anti-causal component. In a bid to do that, you may arrange the divisor in this manner: minus 1.2 z to the power minus 1 plus 0.2 z to the power minus 2 plus 1, and proceed with the division as we did in the last two cases. Don't write down the entire thing, you try on your own. 1 has to be divided by minus 1.2 z to the power minus 1 plus 0.2 z to the power minus 2 plus 1. I have rearranged the terms in this manner. So you try on your own and try to generate terms involving positive as well as negative powers of z. All right. Try it and tell me next day what the result that you are getting. You may write down this result, but I am not sure whether this is correct or not. I was trying, but I couldn't get the time to complete it. So that was about the long division method for getting the inverse Z transform. Now, disadvantage of this method is that you get the sample values of the inverse Z transform, but you don't get an expression for the inverse Z transform. That is the main disadvantage, but it's easy to apply. So in certain cases, it will suit your purpose. Otherwise, if you're interested in the expression, you have to go for the other methods. Now, we are considering power series method, power series expansion method for evaluating the inverse Z transform. In this power series expansion method, there are two classes. One is the inverse Z transform of xz expressed as a rational function that we have considered in the form of long division method. Now the second type is that xz is non-rational function. Xz is some non-rational function. That means it's not known as the ratio of two polynomials in z. If xz is known, is given as a ratio of two polynomials in z or polynomials in z to the power minus 1, then we say that xz is obtained in as a rational function. But if it's not that way, say This is the expression for xz. Log of 1 plus a z to the power minus 1 with magnitude of z greater than magnitude of a. Then how will you obtain the inverse z transform for this expression? Write down these things. You know the infinite series expansion of log of 1 plus a z to the power minus 1. So that knowledge has to be applied here. So for solving such problems, remember that you should just recapitulate your knowledge of the infinite series expansion for different functions of z. It can be log, it can be e to the power z, it can be sine z, like that. So all these series expansion formulae, it should be at your fingertips. Now, for magnitude of y less than 1, the power series expansion for log of 1 plus y. Have you written this down? This is the power series expansion. Log of 1 plus y, it will be summation over n equal to 1 to infinity minus 1 to the power n plus 1 divided by n times y to the power n. In our case, we are having a logarithmic function where y is a z to the power minus 1. So you can use the same formula here. So xz, because it's log of 1 plus a z to the power minus 1, substituting here y with a z to the power minus 1, you get this expression. All right? Minus 1 to the power n plus 1 times a to the power n times z to the power minus n divided by n. So what is the inverse z transform? Inverse z transform is simply that term. The term inside the summation excluding z to the power minus n. So that is the expression for n greater than equal to 1, because thus see here the summation extends from n equal to 1 to infinity. So this is valid for n greater than equal to 1, and it's 0 for n less than equal to 0. All right. Therefore, in a more compact form, xn is minus 1 to the power n plus 1 by n, a to the power n u n minus 1. If you write, you introduce u n minus 1 here, you need not write these two separate expressions. One expression suffices. Write it down. There is an alternative method also that we'll consider next. You can either carry out an infinite series expansion, or you may use some property of Z transform. When you express it in terms of power series, we say that you are obtaining the inverse Z transform from first principles. That is the language that is used. As an alternative method, if this is xz, then first you take the derivative of xz with respect to z. What will be the result? Minus az to the power minus 2 divided by 1 plus az to the power minus 1. All right. Suppose we represent the z inverse of xz by xn. Now, why have I taken the derivative of xz with respect to z? because I want to use the derivative property, the differentiation property of Z transform. What is that? Z of nxn will be minus Z dxz dz. All right. That means it will be, if you multiply dxz dz with minus z, you will get a z to the power minus 1, because this was dxz dz. You are multiplying it by minus z. A z to the power minus 1 divided by 1 plus a z to the power minus 1. Thus, a divided by 1 plus z to the power minus 1, you know, is the z transform of a into minus a to the power n un. What is the z transform of simply minus a to the power n un? What is the z transform? It's nothing but 1 by 1 plus a z to the power minus 1. But there is an a term in the numerator. So this is the z inverse, this is the z transform of a into minus a to the power n un. Did you get it? All right. So you can write it as z transform of a into minus a to the power n minus 1 into un minus 1. A into minus a to the power n minus 1 into un minus 1. All right. Write this down, then I'll proceed. Why did I write it? You have understood. This is z nxn. Simply a by 1 plus a z to the power minus 1, it will be the z transform of a into minus a to the power n un. You have the z minus z to the power minus 1 term. So z transform of nxn will be, instead of n, you have to write n minus 1. So you have to write n minus 1 here and n minus 1 there. The time shift property of z transform. So nxn will be given by that expression. Therefore, xn will be given by this expression. It may appear to you that xn obtained by this method and the xn obtained by the earlier method, they are different. But it's not so. If you try to generate the sample values of xn, x0, x1, x2, x3, x4, all these things, you will see that xn using that expression is same as xn using this expression. Same thing. So that is the case. You may try out for other functions of z, namely e to the power z and sine z. Or sine z uz, whatever it may be. Try out for other cases. Now come to the partial fraction method, which is the very versatile technique of obtaining the inverse z transform. Because you already know about partial z transform, there is nothing very lengthy to deliberate upon. Simply a particular trick a particular important aspect of applying the partial fraction method to functions of z is, I will just like to point out. To understand that, just see here, I have tabulated three functions of continuous time signals and their respective Laplace transforms. All right. On the right hand side, I have considered the uniformly sampled version of these continuous time signals and their Z transforms. So in case of ut, the unit step, what is the Laplace transform? 1 by s. The discrete time version has a Z transform z by z minus 1. In case of e to the power minus at ut, the Laplace transform is 1 by s plus a. For the discrete time version, the Z transform is z divided by z minus e to the power minus a. A to the power tut, this is the Laplace transform. A to the power nun, that is the Z transform. So what is the important fact that you can observe here is that in the numerator of the Laplace transform, there was no term involving s. But here, for the corresponding discrete time signals, there is a z term in the numerator. All right, there is a z term in the numerator. Because of that, what is done here is that, just remember it, this is a very important thing. If you have a knowledge of xz as a ratio of polynomials in z, if you have a knowledge of xz as a ratio of polynomials in z, your first duty will be to obtain xz by z. Then once you obtain xz by z, you expand it in terms of partial fractions. Once you expand it in terms of partial fractions, cross multiply by z to get the partial fraction of xz. That is only when xz is obtained as a ratio of polynomials in z. If you have xz as a ratio of polynomials in z to the power minus 1, then no such division is required. I'll show you in a particular example. So first you write down these observations. What I have written here is that examination of first order functions in table for Z transforms indicate that a factor Z is required in the numerator of these terms. That's why if you have xz as a ratio of polynomials in Z, first you have to obtain xz by Z. Then you have to cross multiply by Z to get the partial fraction expansion of xz. So write this down. Sorry. Have you done it?
No, sir.
No, sir. Sir, done.
Consider a problem. This is the given xz. You have been asked to find out the inverse z transform for these three ROCs. Remember carefully that if I simply give an expression for xz, say I could have given the problem in this way. Just the expression for xz I could have cited. No other thing is mentioned. Simply you are asked to find out the inverse z transform of xz without mentioning the ROCs. Then it will be your duty to identify all possible ROCs of this expression for z and then proceed. For each ROC, obtain the inverse z transform. Here you will see that the poles of this function of z, poles of xz, they lie at z equal to 2 and z equal to 3. All right. If that is the case, and if you use your knowledge of the property of ROC, you can easily identify that there are three possible ROCs here. One is magnitude of z greater than 3, because there must be one pole at least in the boundary of the ROC and ROD. So because for magnitude of z greater than 3, the boundary between ROC and ROD is a circle of radius z equal to 3. Therefore, a pole must lie here at z equal to 3. So this is one possible ROC. Second possible ROC is magnitude of z less than 2. Here on the boundary only one pole lies at z equal to 2 and z equal to 3 in the ROD. Third possibility is a ring-shaped region, magnitude of z greater than 2 less than 3. And here both the poles z equal to 2 and z equal to 3 lie in the ROC and ROD boundaries. There are two boundaries of ROC and ROD in this case, in the second case. And the poles lie at the two boundaries, one at z equal to 2, another at z equal to 3. All right. So how to proceed? Write down the problem, then I'll proceed.
Yes, sir. Done.
Let xn be the inverse z transform of xz. Then xz, first I have obtained it as a ratio of polynomials in z. If I obtain it as a ratio of polynomials in z, this is the expression. Minus z squared divided by minus z. That is in the numerator. In the denominator, you have z squared minus 5z plus 6. So first duty will be to obtain xz by z. If you divide xz by z, here what will you have? The numerator will be divided by z, so you'll be having here minus z minus 1. And in the denominator, if you express it, if you factorize it, you get these two factors, first order factors, z minus 2 divided by z minus 3. Now xz by z, you express it in terms of partial fractions. A by Z minus 2 plus B by Z minus 3. So A will be Z minus 2 into XZ by Z with Z equal to 2. That will come out as 3. And B will be Z minus 3 into XZ by Z with Z replaced by 3. After this multiplication, that will yield minus 4. So A is 3 and B is minus 4. Note it down. Once you have done that, your job is, the major part of your job is over. You've written it. So this is XZ by Z. Now you cross multiply with Z to get the partial series expansion of XZ. Cross multiplying with Z means 3Z divided by Z minus 2. Or you can write here 3 divided by 1 minus 2Z to the power minus 1. Minus 4Z divided by Z minus 3. That means minus 4 divided by 1 minus 3Z to the power minus 1. So now you know the inverse Z transforms of these two terms. But that will depend on the ROC. In what manner will it depend on ROC? If the ROC is magnitude of Z greater than 3, xn, the inverse Z transform, it will be a causal sequence. Therefore, the inverse Z transform of the first term should be a causal sequence. The inverse Z transform of the second term also will be a causal sequence. So you have come across such cases. Xn will be the inverse Z transform of the first term. What is that? 3 into 2 to the power n un. We are simply considering the knowledge of Z transform of function a to the power n un, and 3 is a constant. All right. So in a similar manner, the inverse Z transform of the second term will be minus 4 3 to the power n un. All right. Just see here, I have cited the figure. These are the two poles, one located at, for this particular case, one located at Z equal to 3, another located at Z equal to 2. So this is a circle with radius Z equal to 3. The exterior of the circle is the region of convergence of XZ for this particular case. What will happen in the other two cases? You have drawn it. Second case, magnitude of Z is greater than 2, less than 3. Under that condition, Xn is a two-sided sequence. Before that, let me first consider case 3. ROC is magnitude of Z less than 2. For that case, obviously, Xn is an anticausal sequence. If Xn is an anticausal sequence, the inverse Z transform of both these terms, inverse Z transform of this term should be an anticausal sequence, inverse Z transform of that term should be an anticausal sequence. So what will be the result? For magnitude of Z less than 2, that ROC, first term, its inverse Z transform will be 4 into 3 to the power n u minus n minus 1. Recall, we have obtained an expression earlier of that type of time series or sequence. Second term also, it will, on inverse Z transformation, it should yield an anticausal sequence. So its inverse Z transform will be minus 3 to the power n u minus n minus 1. All right. This is the situation. This is case 3. I am showing you case 3 first. Then I move on to case 2. Let's see here that in this case, this is a circle of radius 2 units in the Z plane. There is a pole at the boundary at Z equal to 2, and there is a pole in the region of divergence at Z equal to 3. So this is the inverse Z transform, anticausal sequence. Now come to case 2. This case. So I am considering that xn is x1n plus x2n. All right. So x1n is the inverse Z transform of that expression. Because magnitude of Z is greater than 2, x1n should be a causal sequence. So what will be x1? 3 into 2 to the power n un. What about x2n? x2n is the inverse Z transform of, just 1 minute, let me enlarge. x2n is the inverse Z transform of that term, this one. Because magnitude of Z is less than 3, x2n will be anticausal. So x2n will be 4 into 3 to the power n u minus n minus 1. So xn equal to x1n plus x2n will be equal to 3 into 2 to the power n un plus 4 into 3 to the power n u minus n minus 1. That is the causal part. This is the anticausal part. So that is about part 3.
Sir, can you go up slightly to
Oh,
x1n?
yes, sure. Here the ROC is a ring-shaped region. Inner radius is at Z equal to 2, outer radius is Z equal to 3. Just see here that there are two boundaries of ROC and ROD, and two poles lie at the two boundaries. Third part I have already done. Because I have expressed xz as a ratio of polynomials in z, I had to divide xz by z before proceeding with the partial fraction expansion. Done it. Just 1 minute. Second, next problem. Xz is z divided by z square minus z plus 1, and it stated that it is the z transform of causal sequence xn. So it's mentioned that it's a causal sequence. You have been asked to obtain xn. Again, you divide by z, divide xz by z, get this expression. Now you try to factorize the denominator polynomial. On factorizing the denominator polynomial, you see that the two poles lie at 1 with argument plus minus pi by 3 or plus minus 60 degrees. So there is a complex conjugate pair of poles in this case. Because there is a complex conjugate pair of poles, it implies that it is the inverse Z transform will be a steady oscillatory signal. Xn will be an oscillatory sequence with steady amplitude. Because the complex conjugate pair of poles lie on the circumference of the unit circle. হয়েছে?
Done.
Now you proceed with the partial fraction expansion. Xz by z, say it's k1 divided by this factor plus k2 divided by that factor. K1, you simply obtain it as 1 by, because what you have to do, you have to multiply xz by z with this z minus e to the power j pi by 3, and then in that product replace z with e to the power j pi by 3. So we get it as 1 by e to the power j pi by 3 minus e to the power minus j pi by 3. That means 1 by j2 sin pi by 3. K2, you need not evaluate it in that manner. If you wish, you can do that. But because K2 will be the complex conjugate of K1, you can straightway write the expression as e to the power minus j pi by 3 minus e to the power j pi by 3. That is same but with a negative sign here, as expected. So now you have to substitute these expressions in the expression for z, xz by z. Then cross multiply with z to get the partial fraction expansion of xz. These are the location of the poles. This angle is 60 degree or pi by 3 radians. This is minus pi by 3. So this is xz. I have substituted the value of sine pi by 3 here, root 3 by 2. So this is the inverse Z transform. Using basic expressions for the Z transforms of this form, some constant into Z divided by Z minus A, which is equal to that constant into 1 divided by 1 minus e to the power j pi by 3 into z to the power minus 1. The inverse Z transform will be as indicated here, 1 by j root over 3 e to the power j n pi by 3 un. Similarly, for that case, it will be minus 1 by j root over 3 e to the power minus j n pi by 3 un. So you combine these two ultimately to land up with a sinusoidal sequence, causal sinusoidal sequence. Next problem, I have given x at a ratio of polynomials in z, and you have been asked to find out the inverse z transform. It's not written here, but because we are considering problems on inverse z transform, it's implied that you have been asked to find out the inverse z transform of xz. Nothing has been mentioned about the ROC. So you have to consider all possible ROCs, and for each case you have to obtain the inverse Z transform. How will you proceed? What will be the ROCs?
Greater than, less than 1, and between 1 and 3, sir.
Less than 1?
Greater than 3 and between 1 and 3.
Are you sure?
And mention them.
You are partially correct. These are the location of the poles at z equal to 1 and z equal to 3. Xz by z, it's z square plus z divided by z minus 1 into z minus 3. Can you expand this right hand side in terms of partial fractions? I have divided by z, then I am getting this expression. So your next duty will be to express it in terms of partial fractions. Can you do that? Do you propose to express it as a divided by z minus 1 plus b divided by z minus 3? What is the condition that the rational function should satisfy? Under which we can carry out partial fraction expansion. What we have on the right hand side is called an improper rational function. The order of the numerator polynomial is same as the order of the or degree of the denominator polynomial. All right. So this is an improper rational function. You cannot straightway express it in terms of partial fractions. If you do it, it will be mathematically incorrect. So what you have to do, you have to express that improper rational function as a sum of a constant and a proper rational function. That is the first step. How to do that? Just see here that by long division, partial wrong division, I have converted it into as a sum of a constant, which is 1, plus a proper rational function, 5z minus 3 divided by z minus 1 into z minus 3. Now, this is because this is a proper rational function. Therefore, you can expand the second term on the right hand side. That means this part in terms of partial fractions. Once that is done, your job is clearly over. So you should expand the second term on the right hand side in terms of partial fractions. So that can be a straightforward task. Express it as k1 by z minus 1 plus k2 by z minus 3. Do you understand what is meant by improper and proper rational function? A proper rational function is one where the degree of the numerator polynomial will be at least less than the degree of the denominator polynomial. If it is not so, we say that it is improper rational function. And for partial fraction expansion, the rational function should be a proper rational function. So that's why we have to do this maneuvering. Now evaluate the values of K1 and K2. Written it. K1 comes out as -1, K2 comes out as 6. So xz by z, it becomes 1 minus 1 by z minus 1 plus 6 divided by z minus 3. So xz is z minus 1 by 1 minus z to the power minus 1 plus 6 divided by 1 minus 3z to the power minus 1. So what is important to observe here is that xz is infinite at z equal to infinity. So that point z equal to infinity should not lie in the ROC. Z equal to infinity should not lie in the ROC. The ROC should exclude z equal to infinity. Case 1. See, magnitude of z therefore will be greater than 3 less than infinity. That is important. Less than infinity. That's why what will be the inverse z transform? What will be the inverse z transform? How do you substantiate that? Both these terms should yield causal sequences. And that term you easily know it will generate an anti-causal. Sorry, it will generate an anti-causal term, yes. What's the inverse z transform of z? It's delta n plus 1 because z transform of delta n is 1. So z transform of delta n plus 1 by the shifting property, time advancing property of z transform, it's z. So xn is delta n plus 1 minus un plus 6, 3 to the power n un. That is the first case. ROC of xz, the second case is magnitude of z less than 1. When magnitude of z is less than 1, what will be xn? Delta n plus 1 plus u minus n minus 1 minus 6 3 to the power n u minus n minus 1. So that delta n plus 1 term will be there. So it is purely anticausal sequence. But this one is a two-sided sequence. Of course, on the left side, there is a single term. So after that, to the left of that n equal to minus 1, xn is 0. Last one is magnitude of z greater than 1 less than 3. So here, corresponding to z, that delta n plus 1 term is there. Just 1 minute. Yes. Then, because magnitude of z is greater than 1, the second term, this one, will be the z transform of a causal sequence. So inverse z transform is unit step sequence minus un. And last one will be an anticausal sequence because magnitude of z is less than 3. So 6 minus 6 3 to the power n u minus n minus 1. These are the three cases. So never, of all these three cases, never the sequence is purely causal. It is either purely anticausal or a two-sided sequence. This is perhaps the last one. Xz is z squared divided by z minus 1 into z minus 0.5 whole squared, and the ROC has been given as magnitude of z greater than 1. Task is simple because only one ROC has been provided. But you should be prepared to find out the expressions for z transform for the other ROCs. See here the term z minus 0.5 whole square is there. As the first step, obtain xz by z. That is the expression. Because that z minus 0.5 whole square term is there, the nature of the partial fraction expansion will be as indicated. A by z minus 1 plus b by z minus 0.5 plus c by z minus 0.5 whole squared. So A comes out as 4.
Sir, in the above example, when the case 1, this is a two-sided signal, so ROC should be rings, but here in the above case 1, ROC is
ROC
more.
is ring shape. That's why it's greater than 3, less than infinity.
It is not purely causal.
It's not
Some
purely causal. If it were purely causal, magnitude of z would have been straightway greater than 3. Because it is less than infinity, it's not purely causal. Because for purely causal sequences, the ROC of the z transform is the entire z plane to the exterior of a circle of finite radius. All right, entire z plane. Here it's not that. Please.
Sir, case 3 is not written. Sir, please.
Case 3 you have not written.
Yes.
So AS is obtained in a straightforward manner. B, the coefficient of that factor, z minus 0.5, it is 1 by 2 minus 1 factorial times the derivative of z of this term, comes out as minus 4. And the C comes out as minus 1. So xz by z is as given, cross multiply by z, and then use your knowledge of standard sequences, z transforms of standard sequences. On cross multiplying with z, you get this expression. The inverse z transform for the first term will be 4un. The inverse z transform for the second term will be minus 4 minus 4 0.5 to the power n un, and for the third term there will be a multiplication by n. Remember, that is the reason why you are having z minus 0.5 whole square. The whole square term is coming here, so it's minus 2 into n 0.5 to the power n un. That is xn. Only one ROC was mentioned. Have you written it? হয়েছে?
Done, sir.
Now there is another method called contour integration method. If you wish, you can study this method on your own, and if you solve problems of inverse Z transform using this contour integration method, you will get, if it is correct, you will get full marks. But we are not, we really don't consider it. All right. Those two methods that I have considered, that is sufficient. If you want to study that contour integration method, you can do that and use it for solving problems. Next topic, now with this knowledge of discrete time signals, I am moving on to discrete time LPI systems. Discrete time systems. A discrete time system is actually one which operates on a discrete time signal to generate another discrete time signal according to some well-defined rule. That is what is meant by a discrete time system. A discrete time system should operate on a discrete time signal to generate another discrete time signal. In that sense, an analog to digital converter is not a discrete time system because the input is an analog signal and the output is a discrete time signal. A digital to analog converter, that also is not a discrete time system because the input is discrete time signal and the output is analog signal. So discrete time signals systems are simply pieces of algorithms, numerical methods, using which you can operate upon a discrete time signal or sequence to generate some other sequence. So first I am moving on to discrete time differentiator. So what do you want to do in case of discrete time differentiator? There is an analog signal or a continuous time signal, and you want to differentiate the signal. Remember, all the systems that we are considering, they are causal systems. All right, you already know about causal systems. So in case of the discrete time differentiator, if you just recall the knowledge of continuous time differentiator, the input is a continuous time signal, the output is another continuous time signal, which is the derivative of xt at every instant of time. So this is the continuous time differentiator. That means at any instant t prime, the output of this continuous time differentiator is the slope of the input signal xt at that instant, t equal to t prime. Now what you intend to do here is that you want to replace the continuous time differentiator with a discrete time differentiator, which will operate on the input signal xt to generate yt. So first there will be an ADC, which I am representing by that sampler, uniform sampler. So now after the digitization or discrete timization, you have this discrete time differentiator. At every sampling instant, the output of this discrete time differentiator will be the derivative of xt at that instant. So at 0 instant of time, y0 will be the derivative of xt at t equal to 0. Y tau will be the derivative of xt at t equal to tau. Y2 tau will be the derivative of xt at t equal to 2 tau, like that. So this is yn tau, dxt dt at t equal to n tau. That means yn tau will be the slope of xt at t equal to n tau, n having values of 0, 1, 2, 3, 4, etc. And because it starts from 0, n equal to 0, it implies that we are considering a causal signal, causal system, or a real-time system, which will do online processing. A stream of data is coming in and they are being processed, the stream of data, so that you have another discrete time signal which represents the derivative of the incoming analog signal at every sampling instant. All right. Then how to do it? How will the discrete time differentiator, proceed. What are the information available? The sample value information that is available and the knowledge of the sampling period is available. So at t equal to n tau, I have drawn here, dotted line represents the analog signal, dotted line, and the red vertical lines are the samples. So at t equal to n tau, say, what will be the slope? This is the slope that I have drawn, the slope. All right. The slope of this straight line will give you the exact derivative. But the slope value you cannot obtain exactly because you have no knowledge of the analog signal. The information that is available to the discrete time differentiator are simply the sample values that have already occurred and the knowledge of tau. So the digital processor, the discrete time differentiator, it will approximate the slope by the slope of the straight lines that I have considered here, the blue straight line. So what is that one? What will be the slope of this blue straight line? It is, just see here, this value is x n tau. This value is x n tau minus tau. So that difference between those two divided by tau. So this is the approximate slope. So that is the algorithm that the discrete time differentiator differentiator for real-time application should use. All right. This is called backward difference algorithm. From the definition of derivative that you have studied in your school level course, what is the definition that you want to, if you want to use that, it should have been x n tau plus tau divided by minus x n tau divided by tau. But in that case, for computing the derivative y n tau, you require knowledge about a future value of x n tau, which is x n tau plus tau. A value of x n tau that hasn't yet occurred. So that would have been called the forward difference relation. So that can be done only for offline signal processing. When all samples have been stored, you can proceed with that forward difference algorithm. But for real-time application, you have to consider this backward difference algorithm. You have to use sample values that have already occurred. So y n tau will be approximately x n tau minus x n tau minus tau divided by tau. Just write down.
Excuse me, sir.
Yes.
Sir, we have our next class from 1 o'clock onwards.
Okay. You just write down this differentiated part. I'll just.
Okay.
Which class?
Microcontroller, BJB.
BJB. Okay.
Sit down.
Hmm.
go up once more. Thank you, sir.
dxt dt at t equal to n tau. Smaller is the value of tau, better will be the approximation. You can easily understand that. Have you drawn the figure?
Yes, sir.
Yes, sir. Yes.
So that is the algorithm given by equation 3. That is the algorithm. As a sequence, you can drop tau. So you can write as a sequence that yn is equal to a0 xn plus a1 xn minus 1. All right? a0 xn plus a1 xn minus 1. a0 is 1 by tau, a1 is minus 1 by tau. Okay,
Can you go
stop.
up a bit?
Yes, yes. Done it.
Yes, sir.
Okay, let's stop today here. Okay, so please let me know the next date of next class. All right. So let's end today here.
Okay, sir. Thank you.
Thank you. Thank you.